The purpose of our project. Although many people are afraid of plane crashes and other more severe disasters, car crashes are one of the most frequent and fatal accidents of all. The Car Crash Analysis Data Science Project successfully utilizes data-driven approaches to gain insights into car crash dynamics and contribute to road safety enhancement. By combining exploratory analysis, predictive modeling, and machine learning, the project aimed to guide decision making and support efforts to create safer road environments for both drivers and pedestrians. The aim of this data analysis project is to develop a predictive model that can accurately forecast different factors of a crash by user-entered inputs. This website has 4 machine learning models that predict different aspects of a car crash. Feel free to look through them to see which one interests you. The visualizations page contains graphs derived from our data that give some overall takeaways from different datasets and some unexpected correlations. We integrated multiple datasets that provide a comprehensive view of car accidents and their associated injury severity. These datasets encompass a wide range of attributes such as accident locations, time of occurrence, weather conditions, vehicle types, driver demographics, road characteristics, and more. But by evaluating these diverse datasets, our project aimed to uncover intricate patterns and correlations that contribute to the severity of car crashes through using multiple machine learning models. The datasets used included the San Jose crashes data from 2011 to 2020, the US accidents from 2016 to 2023, and the City of Chicago data from the crashes, vehicles, and people. About our team, we have Vartan of class of 2026, Kyle of class 2024, Haasini of class of 2026, Yougang from class of 2027, Adelia from class of 2024, and Ethan Wang, our mentor, college class of 2026.
Okay, so for my visualizations, I used the dataset US accidents 2016 to 2023 from Kaggle. And my first visualization had to do with how the time of day affects the severity of an accident. And I found that 35.8% of accidents that happen during the night are of a severity rating of 4, while only 20.3% of accidents that happen during the day have a severity rating of 4, which is a 15.5% difference. As for the severity of 1, 15.5% of accidents that happen during the night have a severity of 1, while 28.9% that happen during the day have a rating of 1, which is a 13.4% increase. And from this, we can conclude that the lack of lighting during the night leads to accidents being more severe. And my second visualization had to do with how the presence of a police station nearby affects the severity of an accident. And similarly, I found that accidents with a severity of 4, the percentage of accidents with a severity rating of 4 more than doubled when the accident was not near a police station. Furthermore, for accidents with a severity rating of 1 or 2 combined, which are the lower severities, made up more than 75% of accidents that happen near police stations, while they made up only less than 50% of accidents that did not happen near police stations. As for accidents with a severity of 1 alone, they made up 41.6% of the accidents near stations, while they made up 24.6% of accidents not near them, which is a 17% difference. And from this, we can conclude that people drive more carefully near police stations. And police stations are also generally located in town and not on or near highways, where people drive faster and less carefully. And because the station data did not include many true values, meaning that most accidents in my database did not happen near a police station, I removed the variable from my model because it would skew the predictions.
So these two visualizations are from the Chicago datasets. I merged them all together based on crash ID. The first visualization on the right, the 3D scatter plot, that's the left, I'm sorry. Shows the relationship between the fatality of a crash, the damage the crash caused, and the number of total fatalities. And from this, we can see that males tend to cause more damage and also die. The visualization on the right shows the histogram of the ages, and we can see that the mean is around 30.
So this graph is from the UK traffic accidents data set, and it's the distribution of accidents by speed limit and is sorted by severity. So this graph holds significant insights for understanding the relationship between two important factors of road safety, speed limits and accident severity. The visualization helps identify patterns in an accident occurred based on different speed limit categories, shedding light on whether certain speed limit ranges are associated with high accident frequencies. As we can see here, 350,000 accidents happened in the 30 miles per hour speed limit, and 300,000 plus crashes were severe, which is unexpected at a lower speed limit and could suggest better safety measures need to be taken within that speed limit range. So this visualization is from the San Jose crashes data set from 2011 to 2020 and is crash type and severity correlation. The graph describes the relationship between crash type and severity. As shown, pedestrian and bike crashes have a significantly higher injury severity rate compared to other types of crashes. Broadside crashes also have a higher proportion of severe injuries when compared to other types of crashes, like rear end and sideswipe crashes. So this model determines whether you're likely to receive an injury from a crash or not. It uses the San Jose crashes data, and my model used the gradient boosting classifier machine learning model to analyze and predict outcomes. The model combines the prediction of several weak learners that are usually part of decision trees to create a strong predictive model. It builds multiple models and progressively gets more accurate as it builds off the mistakes of previous models. The input columns it was given included the lighting, the city damage, the type of vehicle involved, the primary cause of the crash, traffic control, collision type, and the direction from the intersection at which the vehicle was approaching. Using these inputs, the model returns the probability of sustaining an injury from the crash, with 0 being no injury sustained and 1 being injured. This is my confusion matrix, and the accuracy is around 80%. My model is below, and as you can see, each input has a drop-down menu with different options. And as you click the submit button, you get redirected to a results page, which shows the inputs that were provided and the output. It says the gradient boosting classifier predicts a severity rating of 0, which means that no accident was sustained from the inputs given. And it also has a disclaimer noting the accuracy score of about 80%, showing that the predictions aren't always accurate. And this results page is around the same for all the rest of the models.
Okay, since model 1 and my model use the same San Jose dataset and they're both gradient boosting classifiers, the data is pretty similar. So the visualization previously shown related severity to collision type. So I chose to focus on the moderate severities because there's more data available to train. I focused on different variables compared to the first model, such as weather, roadway surface, and what the vehicle was involved in hitting. For distance, there are no units in the dataset, but assuming it's feet, the moderate injuries column actually has the most range from 0 to 8,448 feet. So the max number is set to 8,500 feet. There's therefore a bigger variation in the factors for moderate injuries because of more resulting collision types. When you select the inputs from the dropdowns, you can submit and it will return a true-false statement depending on whether the model thinks you'll sustain a moderate injury from these factors or not. However, this model has an accuracy rate of around 69%, which isn't that ideal, so it might not always be correct.
The third model we did was a neural network. This one used the Chicago dataset, which again was merged based on the idea of the crash. We only used the top 14 columns that were correlated to the output that we were trying to predict, which was crash type. And crash type is a variable that is basically you either had no injury and you drove away, or you sustained an injury, or you got towed due to the crash. And it uses a neural network, which takes in the 14 input columns, then it uses 500 hidden neurons, and then another 500 hidden neurons, and then produces an output with around 90% accuracy.
For my model, I used a random forest classifier. A random forest classifier is a machine learning model that creates various random decision trees, with each one producing an output using the data provided. The forest part of its name refers to how the model combines the outputs of all these decision trees to return a single output value. A random forest model can tackle both classification and regression problems, but for this project, it was used as a classifier. And the database I used for my model was the US Accidents 2016 to 2023 database from Kaggle. And the input variables that the model takes in are air pressure, wind speed, visibility, precipitation, temperature, distance of road affected by the accident, the year the accident took place in, whether the accident took place at night or during the day, the presence of a traffic signal, and the presence of crossing roads. And the machine outputs a severity rating between 1 and 3, with 1 being the least severe and 3 being the most severe. And the model has an accuracy score of about 77%. And as you can see in the confusion matrix here, most of the model's inaccurate predictions came from labeling true 2 severity ratings as 3s. And in this scatter matrix, it should be noted that all the severity ratings are 1 less than they should be. So for example, this 0 here is actually a 1, and this 1 is a 2, and so on. And here are all the variables that the model takes in, and you can try out any of these models on our website. And that concludes our presentation. Thank you for listening.